Okay. Right. Okay, we'll start. Good afternoon all, and wish you a happy new year. Online students, can you confirm whether I'm audible? I new year. I will also check from my end. Can you confirm whether I'm audible? Yes. Start. Okay, nice. Right. Okay. So good afternoon again, and wishing you a happy new year. On 31st also, you were the last batch. I mean, I was doing the last class on 31st until 10:30 වගේ class එක තිබ්බද? paper class එක ඊට පස්සේ හිටියා. Right. Okay, so as I told you that day, right? Now a new year means that's a point that you can restart, right? That's a point that you can restart, which means now we are starting off with a new year, new hopes, new blessings, right? Kind of a new vibe, like a mentally and psychologically factor when a year starts, right? When a new year comes, it's kind of a festive season, and psychologically also we have some kind of a different state, right? So as a point, what you can take from that is that's a good point that you can restart your things if you haven't started yet. If you are already on the track, right? Last day also I told you on 31st, right? If you haven't started yet, this is valid for you. This is valid for you. You can restart from this point onwards, right? If you are already on the correct track, right? So if you feel comfortable with the questions we do in the paper classes, right? So if you can comfortably manage the questions we do, right? Which means you are kind of on the track. So if you are on the track, you can keep up your work, right? Because there is an indication that you are doing good, you are on the track, right? You are doing the things as we need, right? But if you get stuck with the questions, and if you are kind of struggling with the questions, and if you can't recall the previous theory parts, so likewise, then if you feel so, right, if you feel like you haven't done not enough work, which means you have to start, right? So this is a good point for you to start. Here onwards, you got 19 months until your exam, right? You got 19 months until your exam here onwards. 19 months. 19 months until the exam here on. So if you utilize these 19 months to the fullest, definitely your results will reflect it, right? So that is always proportional to what you do, right? Don't expect good results just by being kind of ordinary, right? Ordinary in ordinary results, right? Ordinary results in science stream is usually C and S passes. Those are the ordinary ones, right? So if you need a good grade, so you have to put your effort. You have to do all these things, do all the studies with your fullest effort and everything, with the dedication, everything, right? Now, new year, in this new year, you can set your goal, right? If you haven't set a goal yet, set your goal, right? And when you are setting goals, it's better to set your goals in kind of a monthly timeline. That is better. As an example, let's say now something that you can get an indication about this is marks you have for papers, no? Right? Now, as an example, let's say now for the first paper we wrote, right? Take the MCQ as an example. From 25 MCQs I discussed, you only knew, say, 10 MCQs, only 10. So you set up a goal as by the end of this month, I'm going to increase this mark to 18 MCQs, something like that. That's a goal, right? So try to achieve that goal within the month. Then in the next month, set another goal, right? In the next month, set another goal. I mean, always it should be something in an increasing trend. Then when you do so for all remaining months coming up, so ultimately and eventually you will reach your goal, or maybe you will reach beyond what you have anticipated, right? So that is how it is. So always growth is not linear, right? Growth is not linear, right? Most of you think that the growth is going to be linear. No. If we plot growth against time, growth is non-linear. So in the first parts, there can be ups and downs, and at some point then you will start rising this up. So growth is non-linear. කාටවත් මෙහෙම variations in growth එක නම් this is never going to come there. This is never going to come. This is never going to come for a growth, right? So that is how humans grow, right? There are positives, negatives, ups, downs, and at one point you will come onto the correct track, right? And then it goes up exponentially. Exponential growth කියන එක දන්නවනේ. So it goes exponentially, not linear. That is always exponential. So until you are reaching this point, right, you have to do kind of very much hard work until you are reaching this point. Once you reach this point, then automatically you will increase your the time expenditure when you are doing studies, and your tensions, focus, marks, everything that you will do automatically. But reaching this point is the key here, right? Sometimes when you study now, right, or if you have to do some questions, right, sometimes you may fail like 9 questions and 10 questions, 11 questions fail වෙන්න පුළුවන්. But don't give up. Don't give up, right? Questions 10ක් වැරදුනා නම් think that you are going to do the 11th one somehow. So likewise, we have to do. That is how it goes, right? ඒක දැන් අද වුණාට if it happens today, right, don't let it happen tomorrow. That's the thing. Right? ඒකට වැඩ කරන්න ඕනේ. That is what you need to focus. මේ ටික ටිකක් අමාරුයි. This is the difficult period, and once you reach this point, then you will grow exponentially, right? So for majority, what is happening is, so in this period they are giving up. That is what happens with the majority of A-level students, right? So that is why if you have this focus and the dedication, if you can keep it up consistency, keep it with the consistency, right, you can emerge, you can rise up, because majority is giving up. That's the thing. That's a true story. That's a true story. Majority is giving up. So when the majority gives up, so if you can stay here with the consistency, ultimately you are going to emerge. You are going to pop up from that crowd. That's the thing, right? So therefore, keep that in mind. මෙතන give up කරනවා around 70% වගේ. They are giving up during this period, right? So that is a period that you have to hold somehow, right? You have to hold that period, you have to bear that period, and then once you reach this point, until you are reaching this point, you have to bear up, and once you reach this point, then no one can stop your growth, right? This is valid for not only for studies, this is valid for any other thing as well. Now if you are doing a sport, let's say, now during the first days, maybe the first year, මොනවා හරි දැන් new sport tab, right? හිතන්න you are going to do a sport like, say, other sports, volleyball, right? Volleyball. Now on the first day you don't know anything at all about volleyball. You have just seen how players play. That's it, right? So ultimately only you will grow. දැන් පළවෙනි දවසේ ගියා කියලා එකපාරවර dash ගහන්න පුළුවන්ද? බෑ. එහෙම බෑ. So once you hit the dash, it will go out of the court, right? එහෙම නෙවෙන්නේ. Then that is how you grow. That is how you improve, right? That is valid for anywhere. So therefore, just remember that growth is non-linear, and you have to bear up until you are reaching this point. After that point, definitely you will going to grow exponentially, right? Keep that in mind. And one more announcement. Sometimes you might have seen this. The announcement is, Did you see that I shared a flyer as we are starting a reverse class this year, right? So in the reverse class, now I'm sharing this here because some 27 batch students also inquired about the reverse class, right? That's the reason. For all of you to know, in reverse class, what is happening is there are units in our syllabus that they don't have much links with the previous parts, right? There are links with mechanics. Mechanics all lessons are linked to mechanics, right? So if we know basic mechanics, vectors, Newton's laws, momentum, energy, right? So likewise, they are more linked, friction, right? And there are lessons from the back end that they don't have much links with the previous lessons, right? So in the reverse class, what we are doing is we are taking those lessons from the back end and going to cover one by one, starting from the back end, right? So reverse class is planned to start on 10th of January, right? Start on 10th of January, that is next Saturday, yeah? Not tomorrow, next Saturday at 7. This is a fully online class, 7 to 10, right? So what is happening here is, this is a theory class. This is a theory class. Only difference is we are covering theories in the backward direction, right? And I'm planning to start unit 10 this month. Unit 10. Our unit 10 is properties of matter. Unit 10, properties of matter. So we are starting properties of matter in the reverse class, right? And when it comes to the reverse class, the reason to share this and the reason that you asked from me is because nowadays, you know, there's a trend of now even if you are 27, there's a trend of students that if they are capable enough, if they have the potential, they try to sit for the exam in 26, no, right? Like 1 year before. I mean, that's a minority, but there are such students, right? The currently students are right? They take the exam, they sit for the exam 1 year before, right? That is one option. Or else some students I mean, they like to finish off the syllabus faster and spend their remaining time of maybe 10 months or 11 months or 12 months full time with questions and everything, questions, past papers, model papers, everything, right? So those are the two groups that I need to address, right? So if you feel like you have that potential, because now in the reverse class, you will be covering a different lesson from the back end. And in this class is your regular class now. So here you will be covering the things in the regular sequence, right? From 1 to 11. In the reverse class, that is backwards. So if there's anyone who feel like you have that potential, you have that capacity, potential in the sense capacity, you have the capacity, right? If needed, you also can join, right? You also can join if needed. One set of students that they can take the advantage is if you are planning to sit for the exam in 26, right? 26 only, right? If you need, there are some students, no? The last time, in last time also there were, right? 2 years with the district rank, right? All levels will be in 24 February or March, right? And A levels in 24 November, right? November, December, 24 December, December, 24 December, right? So that is based on your capacity and the potential, right? So if you feel like you have that capacity, right? If you have that confidence that you have got the capacity, if needed, you can join and see. We are starting with unit 10, properties of matter. After unit 10, we will be starting unit 11. After 11, electricity and electronics, unit 8, 9. So likewise, from the back end, we will be covering. Okay. Announcement. And since first day is anyway, that's a open day, a free day, right? To get an idea how this goes, you can join and see if needed, right? On the first day, I'll be giving it on the YouTube live as well, right? Stream එක දාන්නම්. ඒතර ඕනනම් එතනින් හරි බලන්න to get an idea. ඒතර තේරෙනවද කියලා බලන්න. We are starting with properties of matter. That's a new unit, whole new unit, and has connections with mechanics only. Connections in mechanics sector. That's why we are starting here, right? And for this one, for all batches it is open, right? For 26, 27 revision, for all batches it is open, right? The reason to share with you is because some of you inquired, and I know there are students who have that capacity, but they don't have opportunities like this to learn these units. And for such students, you can take the advantage if needed. You can join and see. All right. Okay, let's start. Let's go to the lesson. Sorry? Same. This is the same theory class, same fees, same theory class. Only thing is we are doing in the backward direction. Right? It's a very different side. Flow of the class will be exactly same as this. But units are covering from the back end. That's the thing. Right. Okay. So let's start. So last week we finished friction. Right? So this week we are starting rotational motion. Again, one of the most critical lessons we have in mechanics. And this is actually, the critical means this is actually the point where you are going to start the third type of motion you are going to learn. What are the motion types you already know? Linear, no, right? The first motion we learn in A levels is linear motion, no? Linear motion we know. Second type of motion we learn in A levels is projectile motion, right? And third motion is rotational, we are starting today. And 4 is circular, that is also with the same thing. So during the month, the latter part, we'll be moving towards the circular motion. And the other two motions we have in the syllabus are simple harmonic motion and helical motion, right? So altogether we have 6 types of motions in our syllabus. In A-level physics syllabus, 6 types of motions, right? Helical means spiral motions are there. If a particle travels in a spiral, that is called a helical motion, a spiral motion, right? Those are the 6 motion types we have. Today we are stepping into the third type of motion out of 6, rotational motion, right? Take down the heading, rotational motion. This is also called angular motion. Angular motion. Rotational motion is also called angular motion. Rotational motion is also called angular motion. Okay, listen. So before I explain, any idea that you have what a rotational motion is or what an angular motion is? Any idea you have? Motion in a rotation, with a rotation. Correct, up to some extent, that is correct. Rotation that is rotational motion, right? So try to add some more words or rather keywords. In a circular path. From a point. You mean around a fixed point? Online? Any thoughts? What do you think a rotational motion is? So don't Google or ChatGPT. Just tell me your thoughts. I don't need the definitions. Your thoughts. That's it. Right? Words rotational or angular. What do you think? Any thoughts? An angular displacement from a point. Okay, the point is there. Okay, listen. Something like this. Rotational motion means Rotational motion means if an object travels around its own axis. What is an own axis? If the axis is inside the object, that is called an own axis. As an example, take this sphere. This is a sphere, right? Or say a disk. This is a disk. This disk travels about this point A. Point A is an own point, no? Right? So if it travels about point A, this is how it travels. Say this same object travels about a point like point B. So if it travels about point B, this is how it travels. Is it clear? Very comparative to rotation and revolution of Earth. So we are rotating around our own axis while doing revolutions around sun. Something like that. Right? Own axis means if the axis or the point of rotation is inside the object, that is called an own axis. On. If that is outside, that is called an external axis. Right? External axis. This is also called internal axis. Own axis are internal axis. Right? So if the rotation is about the own axis, that is called a rotational motion. Right? If the rotation is about an external axis, that is called a circular motion. So therefore, rotational and circular are two different words. Right? So therefore, don't say circular with rotational motion. They are completely different. Difference is with this. Right? Again, if I relate this to motion of Earth, right? Rotational motion is about our own axis. And around sun, what Earth does is, that is not a rotational motion, that is a circular motion. That is a circular motion. What the idea? Right? So in a circular motion, this path is also a circle. This path is also a circle. Now here, this rotates only about this, like this. That is called rotation. That is called rotation. About an own axis. Right? If I show you it using this, see? Now if I rotate this like this, this is an own axis. Make an axis. This is an own axis. This is a rotation. If I rotate this like this, this is also rotation because I am rotating about this axis. If I rotate this like this, now about somewhere here, this is a circular motion, that is not a rotational motion. Got the idea? Right? If rotation is about an own axis, or that is also called internal axis, these are the keywords now. First keywords you learn, either own axis or that is also called internal axis. On or internal axis. Such motions are called rotational motions. Right? That is how a rotational motion is defined. That is the definition. And don't mess up with the circular motion, right? That is why I explained you what a circular motion is also here. Circular motion is always when if the object rotates about an external axis only. Right? On point circular motion then. Right? Okay. First write down first point. Motion about the point. Good. Yeah. About the point, it's true. That point should be on point. Okay. Write down. If an object travels around, slash about, if an object travels around slash about its own axis, slash internal axis, slash internal axis, it is called a rotational motion. It is called a rotational motion. It is called a rotational motion. Right? Okay. Look at here. Assume this disk. Assume this is a disk. This disk is connected to this axis. This disk is connected to this axis, right? And we are going to move this disk about this axis like this. Remember one, right? We are rotating this disk about the axis. Now, assume this as the axis. A disk is connected here, and it can be rotated like this, no? Circular motion or rotational motion? Circular motion or rotational motion? Rotational, because this axis goes through the object. So that is an own axis. Rotational, right? Right. An athletic, right? An athletic, say running 400 meters around a circular track. Circular motion or rotational motion? Circular motion. Circular motion, right? Circular track, circular motion. Then point of axis is, point of rotation is, or axis of rotation is somewhere here, outside of the body. That is a circular motion. That's the difference, right? That's the difference. Right. Now, under this heading, we are in rotational motion throughout, and after the end of rotational motion, our next motion type coming up is circular motion, right? So, from this part, you are going to learn two new motion types, right? Then, for your list, you will add these two by the end of the lesson, rotational motion and circular motion, and your list of types of motions is going to increase up to 4, right? 6 is right? From all 6, 4 types of motions are under mechanics, and simple harmonic motion comes under unit 3, oscillations and waves, and helical motion comes under unit 9. Right. Okay, now listen. So we know when we study about linear motion, we had linear motion parameters, no? Remember? So first day of linear motion, I told you we learned parameters of linear motion. Then if we are going to study about rotational motion, then it should also have parameters, no? Right? Without having parameters, how to study a motion? So we have to have parameters. Now, since these parameters are very comparative, we are going to compare these parameters. So first, we will recall the parameters we learned in linear motion again, right? Now, I need all of you to respond. First, tell me, what are the linear motion parameters we learned? Velocity is a parameter. Then if I split into two, initial velocity and final velocity, 2 parameters, right? Good. First one, initial velocity. Initial velocity, right? Then final velocity. What else? Displacement. Now, since now we are going to start the rotational motion, angular motion, right? I will write this as, in exact words, as linear displacement, right? So even though we say displacement, that is actually linear displacement. Linear displacement. The reason to say that way is, right? So here also we have displacements, but not linear. Non-linear displacements are here, right? What else? Time. I will write time later. Then acceleration. For acceleration also I will write it as linear acceleration. Simply, right? Linear acceleration. Now we know these terms with the notations U, V, linear displacement, S, linear acceleration, simple A, and time, simple T, right? These 5, listen, these 5 were the main 5 parameters we had in linear motion, right? In a linear motion. Now, other than these parameters, if I think about something like external unbalanced force, is it linear or nonlinear? Right? Now I'm going to collate everything that we learned so far. External unbalanced force, linear, no? Because there is a vector with a given direction. External unbalanced force is a vector with a given direction, no? So that has a linear property. So therefore, external unbalanced force is also a linear parameter. That is a linear parameter. That is also a linear parameter. Let me Add everything to the list. External, unbalanced force, capital F. What else we had in linear motion? Now, when I say external unbalanced force, then what is coming to your mind? When I say external unbalanced force, what equation or what law comes to your mind? F equals ma, right? And when on F equals ma, then mass also there. No? When you apply F equals ma, simply what I am trying to say is, when you use F equals ma, you use F equals ma only for linear motions, isn't it? Right? Either it is moving in a inclined plane, no, horizontal plane, no, vertically downwards or vertically upwards, so it was linear. It was linear. Then you have used m there. Then m is also a linear parameter. Mass. Simple m. What else? Mass is added, then weight on derives, no? That's a huh? Yeah, put under this one as well, right? And the second thing is that is actually something derived from this, no? And with the holistic view, weight, listen, that's a good question. If you got a doubt why we don't write weight here, weight can be categorized under external balance forces. That is also force, right? What else? What about work? What is the equation of work we used? Work equals force into, right, displacement. Linear or non-linear? It's also linear. Because we were using W equals Fs only for linear motions. So work in linear motion, right? Work, this is in linear motion. W, right? Now, this is what is going to happen. When it comes to angular motions or rotational motions, linear motion. And this is what happens in angular motion or rotational motion. Now, for angular motion also, for the purpose of studying about angular motion, we have to have parameters, right? Now, here the thing is, these parameters are also very much comparative with what we dealt with in linear motion, right? Question? Parameters means variables. So I didn't explain it further today because we have explained it in linear motion. Linear. Idea? Right? Parameters means variables. Right? Right. Initial velocity. Now here what happens is, instead of velocities, here we have angular velocities. Listen, instead of velocity, right, here we have angular velocity. So therefore, this is called initial angular velocity. Right? So you will see why this is being angular. Initial angular velocity. Initial angular velocity. As we use v for velocity in linear motion, for angular velocities we use omega. This is how omega is written. This is not w. This is called omega. This is not w. This is how omega is written. Right? Omega. Right? This is how omega is written. Right? This one is lowercase, this one is the uppercase. Right? Make a symbol like omega. So in Greek letters also, in Greek letters we have uppercase and lowercase letters, no? Simple and capital. Make simple like, make capital like. Right? It is good. Both are omega, uppercase and lowercase. This is used for ohms in resistance. Make omega. This is not W. And initial angular velocity is called omega 1. And this converts as final angular velocity. It is called omega 2. Right? Linear displacement, no? Instead of linear displacement, here we have angular displacement, right? Here we have angular displacement. We'll see how this angular displacement occurs and how this is measured, and there are more things. So first I need to give you is, first idea that I need to give you is how these terms and the parameters are going to be changed when you are going to angular motion, right? Same parameters, but they are adjusted, they are changed as it is matching with the rotational angular motions, right? Angular displacement, angular displacement. Angular displacement is an angle. So therefore, this is denoted by theta. Angular displacement is an angle denoted by theta, right? As linear acceleration here we have angular acceleration. Angular acceleration, right? Denoted by alpha. Denoted by alpha. Time is same because time is not a relative quantity. Time is an absolute quantity, right? For any type of motion, time is same as time, no? That is not going to be different. Time is the only term that is going to remain same actually. Time is same as t. This one, here we had external unbalanced forces, no? Here we have external unbalanced torques. External unbalanced torques. Torque is not TOLK torque, TORQUE torque, right? When a torque, if you have gone through specs in machines, vehicles, automobiles, motorbikes, some motored vehicles, you might have seen this, right? This is called external unbalanced torque, TORQUE torque, right? And the symbol is this. The symbol is called tau. Symbol is tau, and the term is torque, right? The symbol is called tau, right? If you need to see, I'm just saying these names, right? If you are not sure about, if you need to see this symbol, just Google symbol tau symbol. Tau. This is not tau. Again tau. Tau. Symbol is tau, right? May alpha, theta, omega. Those are the symbols, right? Greek. May Greek. All symbols are Greek symbols, right? All symbols are Greek symbols. Okay. Instead of mass, here we have a new thing called moment of inertia, right? Moment of inertia. Don't think what moment of inertia yet, because we have more things to learn about moment of inertia under separate heading, because there are more things about moment of inertia. This is not something that we can just explain in 2-3 words, right? That's a topic actually. That's a topic. So therefore, just know that mass is going to be converted as moment of inertia, and we will learn what moment of inertia in the coming parts, right? And that is I. That is English. I. Right? Work in linear motion. Here we have work in rotational motion or angular motion. Work in angular motion. Work in angular motion. We write same W, but the equation is going to be different, right? So we use same W, same notation, but the equations are different. The reason to write this here is, in the next step, we are going to convert our linear motion equations by using these parameter conversions to rotational motion equations. Got the point? If parameters are comparative, equations should also be comparative, no? There are more new equations also coming, but our existing equations in linear motion can be converted to rotational motion using these parameters, right? That is why I explained this first, right? So just know that work is there in both, notation is same, but equations are going to be different. You will see that in the next part when we convert these to equations, right? Okay, is it clear? Don't think about meanings of these parameters yet, because we will be discussing them one by one. Now you don't know what angular velocity is yet. You don't know what angular displacement is, right? I just said there is an angle. You have no idea at all. What I need to give you was, the idea that I need to give you was, these parameters are going to be converted to rotational motion like this, right? It was what these parameters are by taking one by one. Yeah. No. Possible ones are also there. Different ones are also there. Right? Because as a motion, these two are two types, no? Right? Similarities, there are similarities, but there are differences as well. Similarities will use difference. Right? Okay, take it down. Take it down. So don't we also apply F equals ma for a system like a triangle? But when you apply, you are applying F equals ma only for a selected direction. Then that direction is a linear direction. Right? System can be either square shapes or triangle shapes or whatever it is. But when you are applying for a given object, that direction is linear. Direction is linear. Take down. Yeah, so likewise, ask all questions you have, right? So there are some of you on YouTube as well. So if any questions, you can put it to a live chat, right? I can see. Okay, finish. Take down. So this symbol is called omega, right? If someone needs, this is called omega. Symbol is called omega. This symbol is this, no? This is theta, right? This is alpha. Alpha, beta, gamma. This is alpha, right? These are all Greek symbols. All Greek symbols. Originated from them. That's why. Huh? No, using UV is not going to work anyway because that is already used for linear motion. Then we should have something different. That's the Greek symbols ටික වෙනස් කරන්න නැත්තේ because I mean originated from them no. ඒ කියන්නේ credit එකකුත් එක්ක තමයි. ඒ කියන්නේ දැන් ඒගොල්ලන්ගේ credit එක දැනටත් දීලා තියෙන්නේ. පොඩි respect එක credit එක ඒක එහෙම තියෙනවා. Possible ඒවා convert කරනවා but these are not converted as a credit to them, as a respect to them. And now they are standard symbols, right? Now, if we say omega, everybody knows that omega is about angular velocity. They are standard symbols now. Okay, check again. This side you know, no? Again, initial velocity u, and here we have initial angular velocity omega 1, final velocity v, final angular velocity omega 2, linear displacement s, this is angular displacement theta, linear acceleration here, angular acceleration alpha, time is same, time, external unbalanced force, this is external unbalanced torque, right? Torque, this symbol is torque. Mass m, this is moment of inertia, moment of inertia. I, work in linear motion w, work in angular motion w. Right? Finished? Now this is the thing we are going to do. Listen, this is what we are going to do using these conversions. Now here we know parameter conversions now. Using these parameter conversions, we are going to convert our linear motion equations to respective rotational motion equations. Right? As an next heading, write down equation conversions. Write down equation conversions. Equation conversions. Equation conversions from linear motion to equation conversions from linear motion to rotational motion. From linear motion to rotational motion. Equation conversions from linear motion to rotational motion. Equation conversions. Equation conversions. Okay. See, I'm going to erase this, right? See, let's start with a simple equation. This is what we are going to do here. Look at the board. So I think this will be more clear if you do this on a table, right? So therefore we'll stick to a tabular form, a table form. See. Now again, in this side of the table, right? This side of the table, I'll be writing linear motion. I'll be writing linear motion. This side linear motion, and this side angular motion. Right? Okay, let's start with an easy one. First one. What do you like to start with? V equals u plus AD. Right? V equals u plus AD. Now convert these terms using parameter conversions one by one. Instead of V, we have omega 2 here. Right? For u, initial velocity, initial angular velocity omega 1. Linear acceleration, angular acceleration alpha. Time is same. Right? Omega 2 equals omega 1 plus alpha t. Right? Another kinematic equation, a linear motion equation, kinetic equation, a linear motion equation, you can convert into rotational motion. Right? So likewise, now I will give you the equation this side, you can do the conversions. Right? Start. We'll do one by one. You can start with V. V equals u plus AD. First, let's convert all kinetic equations. S equals UD plus half AD squared. Third one, you know these things. V squared equals u squared plus 2as. 4 is equals v plus u over 2 into t. Let's convert these four. Convert these four. You can raise if any questions. Right, finished. Simple. S equals ud plus half ad squared. Theta equals omega 1t plus half alpha t squared. V squared equals u squared plus 2as. Omega 2 squared equals omega 1 squared plus 2 alpha theta. S equals v plus u over 2 times t. Theta equals omega 2 plus omega 1 over 2 times t. Right? Then 5. F equals ma. Try to convert. F equals ma. F equals ma is a linear equation. No? F equals ma is a linear equation. F equals ma. Instead of f, we have tau here, right? And tau equals I alpha. Tau equals I alpha. Right? 5. Kinetic energy. What about kinetic energy? Half mv squared. 6. Sorry. 6. Kinetic energy. Half mv squared. What about this side? Now, this is actually called linear kinetic energy. This is called linear kinetic energy because now, even though we have been saying kinetic energy, because you only knew linear kinetic energy, no? So therefore, that doesn't matter when you say kinetic energy. Half mv squared, but now you are going to learn more. This is called linear kinetic energy. This is called rotational kinetic energy or angular kinetic energy. So likewise, everything changes now. This is half mv squared, then this side it should be. This is angular kinetic energy, half I omega squared. Right? Since this is just only about a speed, about the velocity, put omega. Right? Initial final meaning, and there's no such meaning as initial and final for this we know, then just omega. Half I omega squared. We don't need to convert mgh, gravitational potential energy, because whatever the motion the object does, gravitational potential is only depend on gravity and the vertical height. Right? Whether it's linear or non-linear, if there is at that particular point, mgh is going to be same. Mgh. What else? 7. What else? What about work? 7. Work. Tell me, work in linear motion. Force into displacement. You can write either as Fs or Fd. Right? Fs or Fd. Here, work in angular motion, rotational motion. then instead of F we have torque S theta. So this is called torque theta. This is called torque theta. Torque theta. Then what about linear momentum? So when we learn linear momentum, we learned it as linear momentum. Linear කියලා කියන්නේම then there is an angular momentum as well. That's why we learn linear momentum. So it is coming under this side. What is linear momentum? P equals mv, mass into velocity. Then angular momentum should be I omega. Right? So likewise, everything is going to convert. What else? How equations can? What else? Impulse එකත් උන convert කරන්න පුළුවන්. Before impulse හොඳ එකක් තියෙනවා. What about power equals, what's the relationship between power, force and velocity? We have proved it. What's the relationship among power, force and velocity? Power, force and velocity. Online, what is the relationship among power, force and velocity? I have proved in the class, and in the paper class also I think we had a question in the first MCQ from that equation. Online, any answers? Quickly. What is the relationship among power, force and velocity? E equals Fv. E equals Fv done? No? E equals Fv. omega dawasa prove kara. How to prove P equals Fv? We know work is F into S, no? Right? So if you don't know how to prove this, this is how the equation is proved. If I need to create power, what should I do for this equation? What is power? What is power? Energy over time. Or we can say work over time. Work and energy are same, no? Power means either energy over time or work over time. Then if I divide both sides of the equation by t, it doesn't do any harm to the equation. Both sides are divided by t. Right? No worries. No any harm to the equation. Right? Now, my required term is created. But we know V over T is, sorry, W over T is, work over time is power. Because this rate of doing work, that is power. Power. And here, I will write this as this. Right? No harm, no? No harm. That is a multiplication. That is a multiplication. You have, let's say, 2 times 4 over 2. You can write the same as 2 times 4 over 2. Right? 8 over 2 is 4. 4 over 2 is 2. 2 times 2 is 4. For multiplications and divisions, no worries. What is S over T? Displacement over time. That's velocity. So which means is P equals Fv. Right? Only relationship among power, force and velocity. P equals Fv. Right? So if you don't know the equation, you better take this note. That's why I wrote. So I'm taking this equation here as the next one. Right? So P equals Fv. Then tell me, if P equals Fv, now these meanings are contextual. This P refers to what? This P refers to linear momentum, but this P refers to power. Right? Power is linear, right? We don't say linear power. That is just power. We call power in linear motion and power in angular motion. Right? P equals Fv, then here it should be P equals what? Torque omega. Torque omega or torque omega. It was a impulse impulse tube. Right? Impulse is Ft. Right? Make it impulse is same. impulse in angular motion, that is torque T. So likewise, these equations can be converted. Equations can be converted. So in angular momentum, or is omega 2? No. Because omega 1 and omega 2 are for final and initial meanings. If your respective equation doesn't have a final initial meaning, use just omega, common omega, right? The meaning is angular velocity, right? Now here, for this velocity, this v here, it doesn't have any final or initial meaning. This is for the mass into velocity. That's the meaning, no? So this is I into angular velocity. Then just omega. T equals F E. T equals F E. Okay. Close the table. Close the table. Close your table from here. Now still you don't know what these terms are. Then you just heard. You just heard. That's it. Now we are going to take one by one and dig deep and see how these terms actually are. What is inside? How these terms are created. So we are going to see now. You just heard only. Equations, you just know that equations are also going to convert. That's it. Right? Otherwise, if I ask you what is angular velocity, you don't have any answer yet. Then answer. But if I asked what is linear velocity? What is linear velocity? Change of rate of change of linear displacement. Rate of change of linear displacement. Okay, let's see. Finish. Linear velocity is done. Right. So first, let's see. What this torque is. Right? Write down definition of external unbalanced torque. Next heading, definition of external unbalanced torque. Definition of external unbalanced torque. Definition of external unbalanced torque. External balanced torque. Right. So always, as you saw comparisons in equations, in linear motion and rotational motion, when it comes to definitions also, most of the definitions are also very comparative. So therefore, if you know all linear motion definitions and all linear motion equations, which means 50% of this thing is already done, no? Because only words are going to change, only terms are going to change. That's it, right? So therefore, the underlying key here is linear motion, right? Last week to go through linear motion because this is very much linked to linear motion, very much linked in the sense comparative. Now, before external unbalanced torque, tell me what was the comparative term we had in linear motion? External unbalanced force, right? First, tell me what external unbalanced force is. External unbalanced force. What is the equation we defined? External unbalanced force. We defined. What is the definition? Anyone with the definition? Just tell me the equation then. What was the equation we used to define external unbalanced force? F equals? No. Online? Not MA. Yeah, MA. MA version use kare. Which version of MA? MA. right? अरे expanded version अगर use करें, अरे मतलब start करेगा मत f equals ma, right? And we use this version. A can be written as v minus u over t, right? Then f is mv minus mu over t. Then tell me, what is the definition of external unbalanced force? What is the definition of external unbalanced force? We have defined in linear momentum. What is the definition of external unbalanced force? Good. Rate of change of linear momentum, right? Okay, correct you at least. Rate of change of linear momentum, because this is final linear momentum. This is initial linear momentum, right? Then mv minus mu is difference of or the change of linear momentum. Anything over time is a rate. Then this is rate of change of linear momentum, right? We have written this definition in red in linear momentum, right? Okay. Now tell me this again. Definition again. Tell me the definition. Rate of change of linear momentum is defined as external unbalanced force, right? Here, this is about external unbalanced torque. External unbalanced torque. See how these things are comparative? How comparative these things are? See, F equals ma. Here we have torque equals I alpha, right? Torque equals I alpha. Then similarly, if alpha is angular acceleration should be expanded. It could be expanded as final angular velocity minus initial angular velocity over time, right? Same thing. Then torque equals I omega 2 minus I omega 1 over time, right? So in the previous equation list, right, you got to know what I omega is. What is represented by I omega? Angular momentum. Then I omega 2 is final angular momentum. I omega 1 is initial angular momentum. Final angular momentum minus initial angular momentum gives change of angular momentum. Anything over time is the rate. So this is defined as the rate of change of angular momentum is defined as external unbalanced torque. Only two words are changed. That's what I said. If you are familiar with the linear motion equations and definitions, when it comes to rotational motion, 50% is done then and there, right? Body comparisons, these are very much comparative, right? Now you better take down both like this. Take down both like this. Then when you study at once, you should be able to study comparatively. These two are not two different things, not two isolated things, right? Same thing, very comparative, right? Take it down. And below, keep some space to write the definitions, right? Meharing, keep some space to write definition somewhere here, right? Keep some space to write definition somewhere here. Finished? Okay, finished? Finished? So write the definition this side, right? Definition here. Okay, tell me again. One last time before writing. Rate of change of linear momentum is defined as external unbalanced force. Write down using red. Definition here. Write down using red. Rate of change of, you are writing the same for the second time. 2 months back, turn back to your notes and see, you have written the same in linear momentum. Write down. Rate of change of linear momentum. Rate of change of linear momentum. Rate of change of linear momentum is defined as external unbalanced force. Is defined as external unbalanced force. So actually you don't need to wait until I say the other side. Rate of change of angular momentum. This side. Definition. Rate of change of angular momentum. Rate of change of angular momentum. Rate of change of angular momentum is defined as, rate of change of angular momentum is defined as external unbalanced torque. External unbalanced torque. Linear displacement විතරයි. අර ඒක ඔලෙල්ස් වලදී කියන්නේ. Linear displacement is the shortest distance between 2 points. ඒක linear motion එකට හරිනේ. ඒතර ඔලෙල්ස් වලදී කියනවා ඉතින් කෙලින්ම එහෙම. Short distance තමයි. But that is only valid for linear displacement. නෑ අරක වෙන්නේ මෙහෙමයි. This is shortest distance no. අරක එන්නේ shortest arc length. Same thing, very comparative. Shortest distance එකක් එනවා අනිත් එක arc length එකක් එනවා. In rotational motion. Right? Coming up, right? Finished. Alright? Rate of change of angular momentum is defined as external unbalanced torque. Right? Okay. Now you know what torque is. Right? Torque done now. Now before today you just knew TAK torque no? Torque karanna. Right. Now let's see what first thing. First let's see what angular displacement is. Next heading, subheading, angular displacement. Subheading, angular displacement. Angular displacement. The rate of change of linear momentum. Good, Amna. Good. Yadursini, good. Tashri, good. Right. I have good correct definitions. Good. Okay, now angular displacement. Now again, I'm going to compare this angular displacement with what? With linear displacement, right? So we have been just saying displacement so far because you only knew linear displacement, but now you already know two types of displacements. Then we have to be specific whether it's linear or angular, right? Okay, so before angular displacement, right? First tell me, what is linear displacement? Linear displacement, right? Say this is point A and this is point B, right? This is point A and this is point B, right? And this shortest linear distance between 2 points is called linear displacement, right? Now I'm going to apply it to here. This is about angular displacement. Angular displacement, right? Now for all the equations coming up here onwards, in the left side I'll be using the linear form and the right side rotational form. You know now, right? Angular displacement. Now in angular motion, let's say this object undergoes in angular motion. And this is a disk, right? This disk undergoes an angular motion about this point, about this axis. Say this point A was here first at t equals 0, like this, t equals 0, and this is t equals t, right? this was here at t equals 0, right? And it was here at t equals t, right? Now this disk has rotated from here to here, no? Right? If there was a, say, there was a mark here at the circumference of the disk, that mark is now here. That mark is now here. There was a mark like this, but at t equals t, the same mark is here. The same mark is here, right? Now it has displaced from here to here in a non-linear path, and exactly that is a circular path. Circle එකක් නේ, not a circular motion. පටල ගන්න එපා. Circular motion is different, right? What I'm saying is, when this mark moves from A to B, right, it has moved in a circular path. Now here it was, this object moves in a linear path, straight line, but here now there is a circular path. In a circular path, the easiest measurement that we can take is angle, right? Easiest measurement that you can take is angle. Therefore, as angular displacement, this angle is measured. This angle is measured. Angle between these two, because displacement, in terms of displacement, it doesn't matter whether the point is 1 centimeter away from this center point, or 2 centimeters away, 3 centimeters away, 4 centimeters away. Still, angular displacement should be same, because this is the shortest angle in between, right? This is shortest displacement, this is the shortest angle, right? That is not the shortest angle. Got the idea? The opposite angle. That is not the shortest angle. So that is not the displacement, right? Shortest angle, right, or the smallest angle between these 2 points is called angular displacement. Clear? Right. Take this down. Angular displacement is always an angle, a rotated angle. Yes. For a disk, that is correct. What you are saying is correct. But rotational motions are not limited to disk, right? For rods also there can be rotational motions, right? For spheres, for cylinders. So likewise with the object, then you have to see there. Now for this example, particular example, I use a disk, right? Write down. Right. So under linear side, write down. Under linear side, write down. Linear side. Shortest distance between shortest distance between linear side, shortest distance between 2 points is defined as linear displacement. Shortest distance between 2 points is defined as linear displacement. Shortest distance between 2 points is defined as linear displacement. Right? This side, shortest angle measured, shortest angle measured with axis of rotation, is defined as with axis of rotation is defined as angular displacement. Is defined as angular displacement, right? Next heading. What do you think the next heading is? Okay, now let's see units and dimensions as well. What are the units of S? Units of S. Meters. Dimensions of S. L. Right? Units of theta. Units of theta. What is theta as a parameter? As a physical quantity? Physical quantity. What is theta as a physical quantity? What is that? Huh? No. Angle. That is an angle. Theta is an angle. Then what are the units of an units? Dimensions. What are the units of an angle? Units. Radians. Right? Radians. First day of units and dimensions. Right? Angles are measured in radians. It's a unit of angles, radians. Then make radians. Degrees, right? Degrees is just a reference unit, not the SI. Then dimensions of theta, dimensions of an angle, dimensionless, dimensionless, dimensionless. Take it down. Now, no dimensions, good. Dimensionless, yes, good. See, now likewise, this is how you should broaden your knowledge. Now, if you know about linear motion and these things, units, dimensions, everything is going to be linked here. Very comparative, very comparative. And for the lessons coming up also, this behavior is same. Everything is linked. That's a sequence. Okay, next heading. What do you think the next heading is? Angular velocity. Angular velocity. Right? Angular velocity. And put theta within brackets here in the topic. And for angular velocity, put omega within brackets the topic. Right? Angular velocity. Right, again, let's compare this with linear motion. What is linear velocity? Linear velocity. Yes, pulling up equation again. V equals delta S over time. No? Right? Delta S over time. Then what is the definition? Rate of change of displacement. Rate of change of displacement is defined as linear velocity. Right? Then here, comparatively, omega should be what? Delta theta over t. Delta theta over t. No? Then omega is defined as rate of change of angular displacement. Simple as that. Rate of change of angular displacement is angular velocity. Rate of change of linear displacement is linear velocity. Right? See how comparative these things are. You have to keep both in mind, both of them in mind. Write down. Right? So under this side, under linear side, write down rate of change of linear displacement. Rate of change of linear displacement. Rate of change of linear displacement. Rate of change of linear displacement is defined as linear velocity. Is defined as linear velocity. Is defined as linear velocity. Other side, right side, rate of change of angular displacement. Rate of change of angular displacement. Rate of change of angular displacement is defined as angular velocity. Right? Is defined as angular velocity. Right? So today in this part, this is all about a comparison between these two. Right? So you are learning these fundamental theories, background in rotational motion means we are always going to compare and contrast between linear and rotational, right? So don't see these two motions as two separate and two isolated motions, right? They are very much comparative, right? So always learn on top what you know about linear motions. That is the easiest way to learn this, because you know something, right? You have gained a certain level of knowledge in a linear motion, no? So use that knowledge here, apply that knowledge here, then you can understand these things easily, right? So find units and dimensions of V and units and dimensions of omega. Send your answers. V number or send me omega, right? Send me units and dimensions of omega. You can write both, right? Just send me units and dimensions of omega. Yeah, what are the units and dimensions of omega? Correct. Correct. Good. Class cut කරන්න class cut කරනොත් ටක් ගාලා බලන්න recording එක. ඒ කියන්නේ මිස් වෙන්න දෙන්න එපා. Because if you pile up දැන් හදිසි දෙකක් තුනක් විතර ආවොත් එහෙනම් ඊට පස්සේ දිගට මිස් වෙනවා. Right? Weekly එක balance කරලා ඉවර කරලා දාන්න. ඒතර week එක ඇතුලේ වැඩේ ඉවරයි. ඒතර Monday start කරන්න පුළුවන් වාට I mean happily you can start Monday of each week. Right? නැත්නම් හැමදාම හිතනවා from previous week I have these things to do. එහෙම එකක් තියෙන to do list එකක් තියාගන්න පුළුවන් නම්. Even මටත් තියෙනවා. to do list එකක් කියන්නේ මම නම් reminders වල තමයි දාගෙන තියෙන්නේ. එහෙම එකක් තියෙන්න ඕනේ. නැත්නම් ඉතින් අමතක කරනවා. Some of students are familiar with sticky notes, right? Sticky notes වගේ එකක් use කරනවා නම් එහෙම එකක්. Sticky notes කියලා කියන්නේ that is a way that you can have a to do list, no? Right? Have something like that. Then you know what are the things you need to complete for the week, right? Academic plan එක වෙනම තියාගන්න. I mean other than the academic plan you have, right? If you have any other tasks to complete during the week, you better either add a reminder on one of your devices, right? Maybe on the computer, or if you are using a phone, or if you are using any other kind of a device, මොනවා හරි එකේ reminder එකක්, or else a sticky note. If you are using a diary, you can write in the diary, right? Because for different students, they have different preferred methods, right? You have to have your own method. Now, basically what I prefer is reminders. That is easy for me, right? Sticky notes වලට වඩා මට ඒක lazy, right? Reminders මට lazy. So මම reminder එකක් දාගන්නවා with the time. Then by the time that I need to complete it, I mean before, reminder එක දාගෙන මම ඒ time එකට නෙමෙයි, sometime before to alert. So lazy. Then I know before it is getting due, I will be notified if I forget it. නැත්තම් තව ඉතින් apps ඕනේ තරම් තියෙනවා. There are like numerous apps you can find in internet as to do lists. ඕන තරම් තියෙනවා. desktop එකේම පැත්තකින් දාලා තියන්න පුළුවන්. ඒතර as a widgets කියන එක දන්නවනේ. As widgets you can add to the desktop. Okay. V ms minus 1 lt minus 1 omega මේක ඔන්න ඉතින් හදලා බලන්න. Units of delta theta over units of time. Angles are measured in radians. Then difference of angles is also radians. Time. Then this is radians per second. RADS minus 1. Radians per second. Right? This is dimensions of delta theta over dimensions of time. Right? We have got answers. Unit. Radians per second. Correct. Radians over second. Yeah, radians per second. ms minus 1, radians per second, t minus 1. Correct. Good. All answers are correct. Then angles are dimensionless. Then we use 1 for calculation purposes, and t is capital T. T minus 1. Right? You have to keep them in mind. Very frequently in MCQs, these things are asked. Right? And one more thing I need to highlight is there is another very popular physical quantity we have in our syllabus having the same dimension as omega. What is it? You have to think. I mean, I haven't covered about it particularly because that is coming under unit 3. but I know, for sure I know, you know it from O levels. Frequency. That is frequency. Right? Frequency. What is frequency? Vibrations per second. So that is a number per second, no? So that is also T minus 1. Very popular, very popular. Dimensions of frequency and omega are equal. Right? Dimensions of frequency and omega equal. Okay. Write down below with red pen. Oscillation. Oscillation, ne? Oscillation කියන්නේ මෙහෙම එකක්. A swing. මෙහෙම එකක්. Oscillation means something like this. This is called an oscillation. A swing. Right? Now, as a definition, if a motion travels back and forth around the same point like this, that is an oscillation. Right? Oh? That is not an oscillation. Right? Any motion travels back and forth from a given point, from a center point, is an oscillation. Right? Like simple pendulum. Don't know? Simple pendulum. Right? Motion travels back and forth from this point. That is also an oscillation. This is also an oscillation. And one other thing is springs. If you drag the spring and release, this happens. Oscillations. Right? Okay. Write down below with a red pen. Dimensions of frequency. Tarshana. Good. Tashri. Correct. Umayma. Correct. Dimensions of angular velocity and frequency. Angular velocity and frequency are same. Dimensions of angular velocity and frequency are same. Right? And again, write down below in red. Dimensions of frequency equals dimensions of omega equals like this, T minus 1. Right. Next heading. What is next heading? Angular acceleration. Right? Write down angular acceleration. Angular acceleration alpha. Right. Same approach. What is linear acceleration? Rate of change of linear velocity. Right? Yeah, velocity. Now we have to be specific. Because now you know two types of velocities. Right? Now it's critical. Right? So you have to be specific. So equation is, as an equation, acceleration is delta v over t, you know. Right? So it is defined as rate of change of linear velocity. Then here alpha should be delta omega over t. Then it should be defined as rate of change of angular velocity. See how easy that is. Okay, write down. Take down, and in the left hand side you can write. Rate of change of linear velocity is defined as linear acceleration. Right? Now, if you have finished writing definitions, find units of both of them and dimensions of both of them. Units and dimensions of that. Easy, right? Rotational motion lazy, ne? බලන්න විස්තර. Right, finished. Right, check your answers. Check your answers. Here, the definition is rate of change of linear velocity is defined as linear acceleration. Right hand side, rate of change of angular velocity is defined as angular acceleration. Right? Okay, after definitions, units of A are ms minus 2. Dimensions of A are LT minus 2. Units of alpha is, right? Now, if needed, you can apply and see like this. I didn't do the application here because this is what we do on the first day itself in units and dimensions. So that's why I didn't write again. Right? Omega, units of omega is RD radians per second, RAD is minus 1 over time is seconds. So it gives, see, it gives radians per square second. Radians per square second. Right? And dimensions of alpha, dimensions of omega over dimensions of time, dimensions of omega is t minus 1. Then t minus 1 over t minus 2. Right? These are the units and dimensions of omega. Okay, clear? Let's move on. All clear? Let's move on. As the next heading, write down relationships between relationships between linear motion and relationships between linear motion and relationships between linear motion and rotational motion. Okay, so under that, write down, let's consider a rotational motion. Let's consider a rotational motion. Let's consider a rotational motion. A rotational motion of radius simple r. Let's consider a rotational motion of radius simple r. Okay, see. Say this rotational motion is going to occur around this point O, right? So this is not a complete disk, this is only a portion of a disk, a part of a disk, right? And initially, let's say this point was here, and then with the rotation, it has been moved to here, right? If this is a part of a disk, so it rotates like this. Then at t equals 0, say, let's say there's a mark like this here, and at t equals 0, this mark is here, right? And at t equals t, this is here, right? Okay, now the first thing is about this. So let's assume, so before that, tell me, what is a term that we can use for the length from A to B? Any term for the length that this particle travels from A to B? Huh? Radius. Not the unit. Term. Any term for the distance or the length. You know, there is distance. Right? This is a distance, no? From A to B, this is not a displacement, there is a distance only. Displacement. So this is a distance. Right? And from circles, you know, in a circle, this is called an arc. N arc. This is an arc, right? So you know a relationship between this arc length, say S, this arc length and the angle. Now angle from here to here. A term for this is, now you know, angular displacement, right? So what is the relationship between, if radius is r, what is the relationship between or among S and r and theta? I have discussed this again on the first day of units and dimensions, right? We have explained this. What is the relationship? S equals r theta. We have discussed, S equals r theta. S equals r theta, right? This S can be written as, radius into theta, subtended angle, right? Making now you know the length of the circumference as what? Length of the circumference of a circle as 2 pi r. That is because what is the subtended angle? 2 phi, 360, right? 360. 360 means 2 phi in radians, because radian phi equals 180 degrees, right? This is the conversion. Radian phi. This is the conversion. Phi radians equals 180 degrees. We did some conversion in the class, right? We did some conversions in the class. So therefore, that is why we say arc length, circumference of a circle is r theta. It should be r into theta. Theta is 2 phi. 2 phi. So that is what you learned as 2 phi r in your O levels. Phi is, yeah, radian phi equals 180. Two different things. Phi in 22/7 is the value. This is a symbol. This is a symbol. From 22/7, what you are writing is the portion, the required portion. That's why. Then it cancels and only this portion comes. Right? Cancel from that portion. Right? And here you can use the symbol phi for 2 phi r. Right? Expand phi expand that you can do, right? But meaning of this phi here is a symbol, a symbolic meaning. The numerical values only that you can do. But this is a symbol. We can radians a symbol. As we have this in degrees, something like that. Right? So what I wanted is this, S equals r theta. Right? This is something we already know from this units and dimensions first day. S equals r theta. Now, this one itself, see, this one itself has a relationship among a linear side of a motion and a rotational side, no, because S is a distance. Distance is anyway not related to rotational motion, right? And I can't say that is linear because that is not a displacement, but both distance and displacement are with linear motion, no. The reason not to say this as a displacement is this is not directional. Not directional. Direction changes. So therefore, we call this instead as a momentarily displacement. For a moment, for a second, for a point, there is a displacement. When it changes, it becomes a distance. Right? So therefore, these equations are applicable for points, for moments, momentarily. Momentarily displacement is r theta. Clear? Right? Momentarily in the sense, for a very small value of S. The same idea you are learning in differentiation. I think you haven't covered differentiation yet in combined maths. If you are doing maths, if you are doing combined maths, have you covered differentiation? Not yet, right? You will learn a lesson called differentiation. I think in grade 13, 13 or 13. There you will learn this idea. For smaller values, very smaller values, this is valid. Because if you consider very small amount from this, that smallest amount is going to be linear, right? Even though there is a circle, if you split this into small parts, this one small part can be considered as a linear part. Then there is a displacement that can be defined as a displacement, but for a small part, no. So therefore, we call momentarily displacement for that moment, for that point. Right now, after this equation, this is what we do. After this equation, right? What happens if we divide both sides of the equation by time? Now this is a momentarily displacement over time. Is a velocity. It's a velocity. And here, can we divide r by time? R is a radius. Idea is this. You can divide by time if that particular quantity changes with time, changes over time. That's it. Now can I divide this by time? No meaning. No meaning. If a physical quantity changes over time only, you can divide it by time. Then R is variable or constant. It's a constant, but theta changes over time. Theta changes from t equals 0 to t equals t. Okay? From t equals 0 to t equals t, R doesn't change, but theta changes. Then I'm going to separate this theta over t. What is theta over t? Angular velocity. Then V equals R omega. Second equation. V equals R omega. Momentarily speed or momentarily velocity with angular velocity. These are the relationships between linear sides and the angular sides. Okay, then doing this again. See, doing this again. V over T equals R is a constant, you can't divide omega over T. Right? V over T is linear acceleration, R is a constant, omega over T is angular acceleration, A equals R alpha. See, these are the actually only three relationships we have. They have a relationship between a linear motion and a rotational motion. Only these three. S equals R theta, V equals R omega, A equals R alpha. Clear? First, take this diagram and then one by one you can prove them and highlight each equation. Now hereafter all three equations are right. Hereafter all three equations are direct equations that we can use. So why cannot we take that as angular displacement? Because angular displacement is an angle. Angular displacement is an angle. This is not an angle. This is a length. This is a length. Right? So go back to the definition I gave for angular displacement and see. It was an angle. Shortest angle. right? Finished? I mean, not here, downstairs, right? So after finishing, we'll go downstairs and have some, right? Finished? Next heading, write down equations for angular velocity. Write down equations for angular velocity. Next heading, equations for angular velocity. Equations for angular velocity. So can you please briefly explain about radians? I think I have missed it when learning units and dimensions. Radians is defined like this. These are definition. It's a definitions. No? Then radians are defined as 180 degrees equals 5 radians. This is the definition, right? A different unit, and radians is introduced as the SI unit of measuring angles, right? That's the thing. That's the definition. Now it is like so 1 kilometer is 10 to the power 3 meters, no? Right? Something like that. 180 degrees is 5 radians with this unit, right? So likewise, all the angles that we deal with degrees can be converted using this to radians, right? Day 1, 27, 28 students are going to learn this in 2 months, because they are having exams in February, then March will start classes, right? So 2 months, 28 now you are old. You are old, right? Not the freshers anymore when the 28 batch came. I mean, it started, right? Then you will be seniors. Seniors in the sense you are old. Not fresh. Fresh means the fresh batch will be 28, right? So likewise, now say you need 30 degrees. 30 degrees can be written as pi over 6. You need 45 degrees, pi over 4. You need let's say 60, pi over 3. You need 120 to pi over 3. So likewise, we can convert those radians degree values, degrees units values to radians, right? Okay, next heading, equations for angular velocity within brackets omega. Equations for angular velocity, right? Right here. For now, I mean, up to here, so far, you know 2 equations about omega. Tell me, what are the 2 equations you already know about omega? Altogether, we have 5 equations. We are going to mention all 5 here at a single place. Now, with the discussion we had so far, you know 2 equations by now. From the definition, we know omega equals delta theta over t. Omega equals delta theta over t from the definition. That's an equation, right? Here when we write, we only write theta over t. The reason is when you measure an angle, right? So by default, it is going to be a difference. No? Angle like measure kara kiyanne inside it, a difference is there. So therefore, it is not mandatory. That is not compulsory to write delta, right? So if needed, you can write as delta theta over t or theta over t. Totally fine. Theta over t. What else? I just said another one. V equals R omega. Then omega equals V over R. Right? Medan the equation here. V equals R omega. Then omega equals V over R. Omega equals V over R. Right? And the other 3 equations, we don't have to prove it here, right? Only the applications are there. The next one, there's a relationship between frequency and omega, right? Prove karan puluwan, manga gonna prove kala pennana. We don't have, but we can prove manga pennana, right? 2 phi f, and this is 2 phi over capital T and 2 phi RPM. RPM is a single term over 60, right? We don't have the proofs of these 3 here, but we can prove using this. We know omega equals theta over t, something additional. See, something additional. omega equals theta over t. Now, what if I use this equation for 1 second? For 1 second, right? Or in other words, what if I use this for 1 rotation? If there is 1 rotation, if there is 1 rotation, theta equals 2π. And time takes for 1 rotation is called periodic time. That's the definition. Time takes for 1 complete rotation is called a periodic time, capital T. Right? So that is how this equation comes. Got it? Then frequencies, number of vibrations per second. No? Then in a rotational motion, there is number of rotations per second. Number of rotations per second. Now, here this is 2π rotations per time t. No? Then if I need number of rotations per second, right? Per second, we can divide this by that time 2π over t, which means this is 1 rotation. This is about 1 rotation. This is about 1 rotation per time of t. We need, as frequency, what we need is number of rotations per second, right? Divide both of them. Number of rotations per second. The number comes here and frequency comes like this. Make opposite because if total time takes for 1 rotation is t, right? For 1 rotation is t, time takes for 1 rotation is 1 over t, no? Right? I mean, for 1 second, time takes for 1 second is 1 over t, no? Right? Say, periodic time of a motion is 100 seconds. Right? Periodic time of a motion is 100 seconds. Then how many rotations are completed within 100 seconds? 1. Then frequency is the opposite idea. Rotations per second. Then divided by 100. Then frequency is going to be 1 over 100. No? Frequency is 1 over 100. Frequency is 1 over t. Therefore, this is 2πf. Right? We don't have, but we can prove. And RPM means, listen, RPM means revolutions per minute. Or we call rotations per minute. Rotations per minute or revolutions per minute, RPM. Boys should know this. In what we call vehicles, motorbikes, cars, in other vehicles, we have RPM gauges, no? RPM meters, right? So that is about RPM. That is the times of rotation, I mean rotations per minute in the engine, RPM. Or RPM ke indicator can RPM goes when you accelerate because the rotations per minute increases, right? This is rotations per minute, no? Same idea. This was rotations per second. This was rotations per second. Then rotations per minute is this into 60. This into 60. Then 2π into 60 over 60. Right? And this gives rotations per 1 second into 60 seconds means RPM. The term is RPM, rotations per minute. So therefore, RPM of 60 comes. Right? This is something additional. You don't have to prove. I just showed you how these equations are coming. Right? They are not coming out of nowhere. They have these kind of proofs, but you don't need. That's why. Right? So if anyone interested, you can take down. Otherwise, you can take down this. These are the all 5 equations we have about omega, which means we don't have any other equations other than these 5 equations in the world for omega. Only 5 equations. These are the 5 equations. Equations, you will go into more depth in higher studies, but only 5 equations. Take down, right? I'll come to you. Take it down. Then after this, we will introduce terms. So take it down.
Since the lines are equal, which is AC and DC, since the lines are equal in magnitude, okay, magnitude of magnitude, therefore the vectors are equal now. magnitudes are equal, the vectors are equal. So
T is a notation, right? If you mess up, this is not dimensions of T. Capital T is a notation. Notation of periodic time. Label of periodic time. Right? Label of periodic time.
Because of these two magnitudes, right?
Write down.
Why? This is completely wrong.
And again, hereafter, you should have gone through all these things and you should be able to recall everything, right? Now, when I ask, tell me 5 equations of omega, here, then you can't stay idle as you know nothing. Right. Now, this is one relationship that we need to need for the proceedings. So, therefore, I will mention this here, right, with these two, right, easily, just by comparing these two. Omega equals 2 phi f, omega equals 2 phi over t, then f equals 1 over t. No? It is coming because omega equals omega. Omega equals omega, which means from these two, 2 phi f equals 2 phi over t. 2 phi to 2 phi cancels. F equals 1 over t. This is another derived equation that we will use more frequently other than these 5 equations. Frequency is always 1 over periodic time. Frequency is always 1 over periodic time.
You can't solve any question.
Yes. Okay. Now we are going to introduce these terms. Introduce these terms one by one. Right. All the equations are for omega. No need to introduce omega. Now we know what omega is. First one, theta. Simple T and capital T are two different things. Be mindful when you are writing. Right. What is theta? Angular displacement. Write down. Introduce terms. Theta. Angular displacement. Introduce terms one by one with me. First one, theta. Angular displacement. Theta, angular displacement. T. Simple T. In this equation, simple T. Time. Simple T. Time. Huh? That coming. V here. Listen. There is linear velocity. Listen. But I told you there is a instant velocity, no? Momentarily velocity, no? Right? So therefore, for this, there's a nice term now. Always a momentarily velocity is having a tangential direction, no? Isn't it? Because now again, if you think further about the same example I gave you, if you think of the displacement here, direction of displacement is like this for that moment. Then velocity is also like that. Acceleration is also like that. Then this is none other than a tangential direction. Got it? Many small parts. Now, when you consider these small parts, see, this direction is tangential along a tangent. You know what a tangent is? Along a tangent. So therefore, this is called tangential velocity. Tangential velocity or instant velocity. Right? Write down V. Tangential velocity. Tangential. Tangential. See?
There are two components.
Tangential velocity. Tangential velocity slash instant velocity. Tangential velocity slash instant velocity.
We have a vector
Or radius of rotation. Radius of rotation. Then 2 phi. Then on F. What is F? Frequency. Frequency. Now, in terms of a rotational motion, what is frequency? So, in terms of a wave, you know already. In terms of a wave, frequency is vibrations per second. In terms of a rotational motion, frequency is rotations per second. Right? Within brackets, write down frequency within brackets, rotations per second. Frequency, rotations per second. Right? Rotations per second. Then capital T. Capital T. What is capital T? periodic time, periodic time, periodic time. This is also called period. Periodic time, that is also called period. Periodic time, that is also called period. Within brackets. What is period? What is periodic time? I explain. Time takes for one complete rotation. Time takes for one complete rotation. Within brackets, time takes for one complete rotation. Time takes for one complete rotation.
Point of the correct.
What those are? Thanks. Time takes for one complete rotation. So likewise, if I didn't see the chat, it's good. You can answer if you know, right? If there is something related to the note, right? For sure, you know. Even if one misses, right? Then within brackets, time takes for one complete rotation. Then RPM. This is a single term. RPM is a term. RPM is a term. RPM. Right? What is RPM? Rotations per minute or revolutions per minute. RPM is valid for circular motions as well. That is why it says rotations or revolutions. For rotational motion, it's rotations. For circular motions, it is revolutions. There are similarities and differences in rotational and circular. Right. RPM, write down rotations per minute. RPM rotations per minute / revolutions per minute. Revolutions per minute. Right? So that word explains it. No, so nothing to write again. Rotations per minute. Okay. Now, by the way, you need to 6. Right. Okay. Then it's 6, 549. Okay. Right. All right. Listen now. The next part coming up is now so far you know about omega and you know how to write magnitude of omega. But the thing is, I didn't discuss anything about direction of omega yet. Right? So in linear motion, it was very straightforward about the direction. But here, that is not going to be the same. Right? So therefore, we are going to discuss about direction of omega separately. Write down as an next heading, direction of angular velocity. Direction of angular velocity. These are the magnitudes. These are the magnitudes. Right? Angular velocity, is it a vector or a scalar? It's a vector. Because angular displacement is a vector. Angular displacement is also a vector. These are vectors. All angular displacement, angular velocity, angular acceleration are vectors. Because they came down, they broken down from linear parts. They are vectors. Similarly, they are also vectors. So therefore, omega has a direction. So let's see how direction of omega is defined. Right? Not as easy as and same as linear motion. Right? Okay, this is a difference. Right? Direction of angular velocity. So before that, tell me how many main directions we have in physics? Or rather in science, how many main directions? Okay, answers 2 කිව්වා, 4 කිව්වා, 8 කිව්වා. What else? Online 4 main directions. I'm not asking how many directions, right? How many main directions we have in physics? 2, 4. Still, I didn't get the expected answer, correct answer. Anyone? How many main directions? About these main directions, you are getting some sort of an idea in O levels. somewhere around magnetic fields මොනවා හරි තියෙනවනේ ඕලෙල්ස් වල. තියෙනවනේ. Faraday's laws. එහෙම තියෙනවනේ. Somewhere around there. You are learning this. Yeah, using this. So ඒ වගේ ඒවා තමයි. Finally, it's 6. It's 6. What are the 6 main directions? Yeah, we got the correct answer finally. It is 6. What are the 6 main directions? This 4 we already know, right? What are these directions? Right? Grade 1. What is the direction? North, නෙමෙයි. I'm not referring to මොනවාද ඒකට කියන්නේ geographical directions. Right? What is this? Vertically upwards. This is vertically downwards. Horizontally rightwards. Horizontally leftwards. What else? What are the other two missing here? What are the other two missing here? Cross and dot. දන්නවනේ. This is inwards. This is outwards. These are the main 6 directions we have. Right? Upwards, downwards, horizontally rightwards, leftwards, inwards, outwards. Right? ඒක මේක යන්න ඉන්න බෑ. Right? So if you don't know, take this down as a note if you don't know. Right? Otherwise, you have to know all 6 directions here on, because we are going to deal with all directions now. And when dealing with these 2 directions, imagine 3-dimensionally, because inward and outward directions cannot be drawn on this plane, no? Because inward and outward directions are perpendicular to this plane, like this. Is it clear? Right? මේක වුණා මෙහෙම පෙන්වන්න පුළුවන්. Do you have any like lengthier planes? එහෙම නැද්ද? Something like this. I don't know whether it's that visible. If you are doing chemistry, have you drawn Lewis structures? Pens වලින් පුළුවන් නේ. Give me 3 pens. මේක pen එකම ගමු. ඒතකොට online එකට පේනවා. See, something like this. These 4 are the 4 main directions, right? These 4 are the 4 main directions, right? Right, it's clear now? These 4 are the 4 main directions: vertically upwards, vertically downwards, horizontally rightwards, horizontally leftwards, and these are the other 2 directions, right? On this plane, this is outwards, this is inwards, right? එහෙම තමයි your directions ආයි තියෙන්නේ. These are the 6 main directions, right? So imagine 3-dimensionally, because we can't draw a 3-dimensional diagram on a 2-dimensional sheet for the diagrams as the diagrams, right? So therefore, that is all about an imagination. That is all about an imagination when you deal with these diagrams, right? Okay, these are the 6 main directions, right? If anyone needs, these are the 6 main directions, right? Vertically upwards, right? Vertically downwards, horizontally rightwards, horizontally leftwards, and then inwards and outwards, right? Using a cross and a dot, right? These are the symbols for inward outward directions, cross and dot, right? The reason to draw a cross and a dot for these 2 directions, reason is this. This is an arrow. This is an arrow, right? So when we draw a proper arrow, right? This is how a proper arrow is, no? Movies වල එහෙම තියෙන. This is how a proper arrow is, right? මේ ජාතියේ මේවා දෙකක් තියෙනවනේ, like this in perpendicular planes. When this arrow goes away from us, what we see is the tail of the arrow. So in the tail of the arrow, this part is there, so we see a cross. When this arrow comes towards us, what you see is this head. Head is a point. That's why we draw this, right? ඒත් arrow එකක් තමයි. That's also an arrow. Okay. Listen now. Listen. Now, for direction of angular velocity, there's a rule. For direction of angular velocity, there's a rule. So one thing you should know moving on here onwards is direction of rotation and direction of angular velocity are 2 different things. Direction of rotation and direction of angular velocity are two different things, right? So the relationship between those two is given by right hand rule, right? I think you have come across the word right hand rule, not Fleming's. Not Fleming's right hand rule, that is a different one. That is this, no? This is just right hand rule. Just right hand rule, right? That is also called Maxwell's screw rule. Same thing. Yeah, same. Yeah, Maxwell's screw rule is also called right hand rule, right? Not Fleming's one, that is a different one, right? Fleming this is called right hand rule, or also called Maxwell's screw rule. And now here in physics we don't use Maxwell's screw rule because that is kind of, the word is kind of expired, isolated, obsolete. Therefore we don't use, otherwise both are same, right? Write down first point. Direction of angular velocity. Direction of angular velocity is given by right hand rule. I have explained you right hand rule. Where? I have explained right hand rule. Then what is right hand rule? Where did I explain about right hand rule? Online? Where did I explain about right hand rule? Force moments. One place is force moments. There are more. Micrometer screw gauge. Where else? Sperometer. Right? Same thing. Same right hand rule. Right? Same right hand rule. Explaining for the third or fourth time, I guess. Maybe third. Right? So this is a right hand. So I draw this same diagram. They are in micrometer screw gauge also. Right? How many fingers? 4. Okay. Now here it is like this. See, when these fingers are directed towards the direction of rotation, this direction gives direction of omega angular velocity. Right? So see, same right hand rule but different applications. For any thread, right hand rule is used, right? For that also, that the reason to use threads in right hand direction is, the tying up direction as rightward direction, clockwise direction is, the reason comes here in rotational motion, because a screw is a rotation, right? So everything will be explained here in rotational motion. Now, so far what you know is, we use right hand rule in micrometer screw gauge, that's a screw, right? And we use in sperometer, that is also a screw. And in force moments, I explained direction of force moment is also given by right hand rule, because direction of force moment decides a rotation. No? Everything related to rotations. Now this is angular velocity. 4 things now, right? Take down quickly. Did I mention the first point? As direction of angular velocity is given by right hand rule. Right? If needed, you can mention it within brackets as Maxwell's screw rule. If needed, if you are familiar with that, but in here we'll be sticking to right hand rule. Right. Okay. Take down the diagram, and now since the students need to pray, we will take the break now. After the break, we'll do few applications and see how the direction is determined when the rotation is given. Right? Now it's 6:02. Take a break of 10 minutes and come back. Take a break of 10 minutes and come back. 6:02 to 6:12. Right? Take a break of 6 minutes, 10 minutes and come back. Right. Micrometer, yes. 7. So does the direction of angular velocity change or not? It changes if direction of rotation changes. It changes if direction of rotation changes. Nathanne. If the direction of rotation is same, direction of angular velocity is same. What is it? Chess. Scramble is also a good game. I mean, if you need to practice vocabulary, scramble game එකක් තියෙනවා. Vocabulary puzzles ඒකත් මාරු. And there was another game as 2048 before එක තාම තියෙනවා. තියෙනවනේ. ඒක මම play කරලා තියෙනවා සෑහෙන්න. ඒකත් මාරු. To increase your kind of decision making and analytical thinking sides, right? ඒකත් මාරු. 2048. ඒකත් මාරු. So even though it says it's 2048, it is not going to end after reaching 2048 tile. ඒක ඕන තරම් ගන්න පුළුවන්. Right. Right. So write down below. We'll see some examples. As an example, write down. As an example, write down. Right? Example. Write down the directions of omega. Write down the directions of omega. Write down the directions of omega in following occasions. Write down the directions of omega in following occasions. Write down the directions of omega in following occasions. Write down the directions of omega in following occasions. Right? Occasion 1. See, this is a disk, and what we mark here with this arrow is the direction of rotation only. There is not the direction of omega, right? So one point most of the students are like missing up is most of the students think that when this direction is given, right, they think that direction of omega is given. No, this direction of rotation only. There is direction of rotation only, right? Okay, then direction of rotation is given, and sometimes, so with this omega is also put like this, but that doesn't mean this is the direction of rotation. Okay, sorry, this is the direction of omega, right? This is only the direction of rotation, right? Can you try the first one? Or should I explain? Can you try first? Or should I explain? This is the second part. So in front of this, you can mention the direction. Come on. Why? Cool. So you have to apply the right hand rule, and listen, when you apply right hand rule, make sure that your right hand and this given diagram is on the same plane like this. Look at here. I'll explain the first one. Right? Look at here. I'll explain the first one. Now, this diagram is on this vertical plane. No? This diagram is on the vertical plane. Then when you apply, this diagram is on the vertical plane. Look at here. Diagram is on the vertical plane. When you apply right hand rule, so first thing is you have to take out your right hand. Right? Right hand rule like left hand again, right? In any case, if you switch these two, all directions are going to be opposite. All the directions are going to be opposite. So first thing is you should know what your right hand is, right? So how to find the right hand if you don't know what the right hand is? Huh? Checking YouTube. Any other easy method? What is the easiest way of finding right hand if you don't know what right hand is? No, you can stand still, right? Stand still, and you can raise your right hand. Then raise hand is right hand, right? Okay, then first take your right hand and or left hand. You are done now. Again, doesn't matter whether you are left hand or right hand. Either way, you have right hand. No? You have to have the right hand. Again, left again, left again, right? Summer cut either comfortable when Urdu attack තියෙනවනේ එහෙම එකක් නෑ හොඳේ දෙකෙන්ම දාන්න ඕනේ right hand එක ගත්තා right then pan තියාගෙන එහෙම කරන්න එපා take out the right hand and make sure that your right hand is on the same plane with this like this මේ see right hand එක මෙහෙම තියෙන්න ඕනේ on the same plane. Now since your diagram is on the book, keep your right hand on the book, then only you can see this properly. Now keep the right hand on the plane and direct these fingers, 4 fingers, to the direction of rotation. See, like this, and check the thumb. Look at here. Check the thumb. Okay? Now it is satisfying. No? What is the direction of thumb now? Outwards. So therefore, direction of omega here is outwards. Got it? One common mistake students do is right. Diagram is somewhere here and checking the right hand somewhere else like this. What idea to which direction that is, right? Again, now if your book is here, apply the right hand rule on the book like this. Keeping the book on the table, don't apply the right hand rule somewhere else like this. Not going to work, right? Not going to work. Always make sure your right hand is kept on the same plane with the diagram. Right? Now, my plane is vertical. Your planes are horizontal. Right? So likewise, you can do. First one. What's the direction now? First one, right? First one. This is how you apply. Apply kala purdu enna one. This is not something that you can imagine, right? Even I apply right hand rule whenever I need. Imagine karanna bෑ. You have to apply, right? Apply it like this, and මේවා හොඳට පුරුදු වෙන්න ඕනේ. සමහර කට්ටියට මේවා කරගන්න හැම බෑ. වරනේ මේ නැත්නම් ඉස්සරහට magnetic fields ගන්න බෑ. When we go to magnetic fields, right? We have these kind of rules with 3 directions. Here this is only 2, right? 3 directions එක දාන්න ගිහලා මේවා cramp කරගෙන අන්තිමට එන්නේ. Right? Apply කරන්න පුරුදු වෙන්න. You have to make this a practice. I mean, make it a practice when you apply, right? Make the right hand rule. Make a right hand rule. See? May apply kara like this. Direction of rotation is this. So direction of thumb is inwards. Direction of omega here is inwards. Cross. Got it? Clear? Third occasion. Now try these occasions one by one. Third scenario. This is a disc. This is a disc. This is a disc. Disc is connected to this axis and rotates in this direction. 4. This is a disc. You can try one by one. Connected to this axis, and this rotates this way. Then 5. This is also a disc connected to this axis, rotates this way. Five. Oh. Draw the arrow. Draw the arrow. Direction is arrow. These two are also arrows. You know, these two are also arrows. So, direction එක ගහන්න arrow එක ගහන්න direction එක. If that is upwards, draw an upward arrow like that. Okay, finished? See? This one. This is the plane of the object now. This disc is horizontal. You can imagine, no? This is the thickness side. So disc is horizontal. Disc එක තියෙන්නේ මෙහෙම. Disc නැද්ද disc? Disc is like this. So it is going to rotate this way. Right? So disc is like this. Then see, direction of rotation is this. Right? Direction of rotation is this. So likewise, always the diagram, direction on diagram, man. Right? Direction of your hand should align like this. Right? These two should align. Then thumb is upwards. No? Direction of omega is upwards. Right? Upwards. And here, see, direction is like this. Direction of this arrow is like this. So thumb is downwards. Direction of omega is downwards. Right? Here, this rotational direction is like this. It should be aligned by the time you apply. Right? When you apply, otherwise, it could be wrong. See? Like this. So it is downwards. This omega is downwards. This axis. Downwards the axis. Alright? That's fine, that's fine. You can write the direction at any side, that doesn't matter, right? Or even outside of this, that doesn't matter. That is along the axis upwards. That's the idea. Along the axis upwards, right? Okay, now you know how to find direction of omega, but now what about direction of alpha? Not the same, not the same, but we can make use of this idea when finding direction of alpha, right? So therefore, there's no any rule to find directions of alpha because alpha is given by delta omega over t, no? That's a change of a vector, right? And using this knowledge, we are going to find directions of alpha next, right? Write down direction of angular acceleration, direction of angular acceleration. Rule is only for omega. Rule is only for omega. Rule is only for omega. Right? Okay, it is. See, now let's consider this kind of a scenario. Right, we are here. Let's consider this kind of a scenario. This is a disk, and disk is rotating in this direction with omega 1, and it increases its angular velocity up to omega 2, and omega 2 is greater than omega 1. Is it an acceleration or a deceleration? Acceleration. This is an acceleration. Then that should be an angular acceleration. Right? This scenario is given. And let's say, look at here, I'll explain the first one only, and we'll give you the second one to do by your own. Do by your own. Right? Look at here. Now, we know acceleration is given by delta omega over t now, which means angular acceleration is omega 2 minus omega 1 over t now, right? Now from this, time is a scalar. Omegas are the vectors, which means direction of acceleration is entirely dependent on direction of omega, right? So therefore, direction is, to find the direction, just to find the direction, considering directions of omega is enough. Is that clear? Time is a scalar, right? So let's find the directions of omega now. What about the direction of omega here? Upwards, right? Upwards. We know in vectors, a vector can be represented using arrows, and direction of arrow is the direction of vector, and length of the arrow represents magnitude of the vector, right? Now this omega 2, no, omega 2 is greater, then I will use an upward arrow like this, minus omega 1 omega 1, that is also upwards, but that's a smaller value like this, just to get the direction. Then upward this vector minus upward vector, the resultant is also going to be upwards, which means direction of angular acceleration here now is upwards. Is that clear? Right? Take it down, and we'll give you another example. Second one. Rule is only for omega. We don't need a rule for alpha because alpha is this. Time mega one, time is a scalar, right? The reason not to consider time is a scalar. Scalar quantity. Time is a scalar quantity. Time is a scalar. Right, this one. Second example. Okay, in this second scenario, is it an acceleration or a deceleration? In the second scenario, that's a deceleration. Right, try second one. Try second one. Now today, today we are going to finish off the day with the completion of all these theories in rotational motion, which means now next day we are starting from the point we left off here, no? Which means everything that we discussed so far will be coming into applications next day. Next day, it will be a full day with the applications of this, right? Other applications, I didn't discuss any applications today yet, right? This is still the foundation required. This is a foundation. Now, compared to the start, at the beginning, you didn't know anything at all about rotational motion. But now, when I say angular velocity, then you have some idea. When I say angular displacement, then at least you know, right? This is the foundation. This is the foundation required, and all the theory parts are done here. All the theory parts are done from here, and next day we are starting the applications, right? So go through everything before you come to the next class. Okay, what's the direction? Outwards. Madhi? Arkam? Online? What about the answers? Second scenario. Thank you and good night, sir. Outwards. Tam here, now it's not finished yet. I didn't finish the class yet. Inwards. Calculation you have to do the math and take it, right? Outwards. Okay, let's see. Inwards. Right. Okay, let's see. See, second one. Alpha equals omega 2 minus omega 1, 14, right? Then simplify these directions of omega 2 and omega 1 because time is a scalar, right? Or either 1 or else don't write anything. Omega 2. Omega 2 direction is, what is the direction of omega? Outwards, sorry, inwards, right? Inwards, cross, right? Cross. Then to represent the magnitude of the vector, I'll be using different sizes of crosses as arrows. Then this one is omega 2 is smaller, no? A smaller cross, right? Minus omega 1. What is the direction of omega? Cross or dot? Lazy, tell me whether cross or dot, right? Know that it is inwards and outwards, but for the ease of using this, right? How we call this is as cross and dot. Cross and dot, that's it. Cross and dot. What about this? Cross, but the value is greater. Value is greater, then it is like this, right? Alright. Now, if you directly didn't see this, use rules of vectors. Make that known. Vector AB can be written as minus vector VA. Vectors. Then I can write this vector as plus dot, no? Plus outwards. Now, plus outward one is added with a smaller cross. Are they same directions or opposite directions? Opposite directions. And outward direction is greater. Then the resultant is going to be outwards. Resultant is going to be a dot. Resultant is going to be a dot. Right? Method simplify, that's fine. Now, if you can simplify just from here, because what you are getting from here is minus cross, no? Minus cross means there is also outwards. So likewise, you have to simplify. So y is t equals 1. What is t equals 1? No directional meaning, not t equals 1. No directional meaning. So if there's no meaning, we put 1 for the calculations. No? If no dimensions, 1. If no units, 1. Right? If no direction, 1. So likewise, that's no need to write. I mean, not a necessity. Not a necessity. This is how directions of alpha is determined. This is how directions of alpha is determined. Right? It's okay, no need to say sorry. අර ක්ලාස් එකෙන් දුවන්න බලාගෙන ඉඳලා තියෙන ඉවර කරන එක. Right. Okay, raise your hand if this is clear. Very important things, find in direction of omega and find in direction of alpha. Right? මේක නෙමෙයි direction එක. ඕක තමයි ටික දවසක්කදී අමතක වෙන්නේ. Right? අද කරනවා. Again after 2-3 weeks when I ask about the direction of omega, don't say this, this is the rotational direction. Rotational direction and direction of omega are two different things. Right? Okay. How many in online? Only 2? Raise your hand if it's clear. 3, 4, 5. Okay, it's clear now? Right. Okay. Right. So if you confused in the last one, right, I'll explain again. Listen before winding up. Omega 2 was the smaller vector. Direction is cross, right? Smaller cross. Minus omega 1 is the higher greater vector. Direction is cross. So higher cross. Minus this thing now, right? So from this, if you can directly see this as a negative value is going to remain from this, which means that's a negative cross value. Negative cross value is equal to a positive dot value. No? That is one way. Or else, if you didn't see it from here, you can try this way, as I did. Right? Cross and negative dot, sorry, negative cross can be written as a positive dot using this rule. Vectors. Vector AB is minus BA. No? Then if this is a negative cross, it can be written as a positive dot. Positive dot. Then positive dot can outward direction, a higher value added with this one, added with this one. Make the step back. If you didn't get this yet, you can rewrite this as negative dot plus this. Simplification of these two is for sure is going to be a dot. Same direction. So likewise, this part is a vector simplification. I mean, using knowledge of vectors, using knowledge on vectors, right? Using knowledge on vectors. And the new thing you learned here is the right hand rule. That is not the vectors. Once you apply the right hand rule, you will get the directions. Then hereafter, that's a vector simplification. No. When you write the answer, you have to write the direction, exact direction. Then the final answer here is outwards. Final answer here is outwards. Final answer here is vertically upwards. Right? Final answer here is vertically upwards. Vertically upwards. And final answer here should be outwards. Right? Don't write in the final answer as negative cross. Right? Then you have to rearrange it and write it as the outward. Alright? Alright. So from here, the theory parts are done. The foundation theories. I mean, this is not the end of all theory parts in rotational motion. Rotational motion is not that small, right? Rotational motion is kind of a large lesson, right? Not that small. So rotational motion theory is needed for the first type of applications we have is covered now, right? Rotational motion theories we need for the first type of applications are covered for the first type, right? So next day we'll be starting all the applications as usual, starting from the simple one and the simplest one, and we'll be moving towards all the advanced applications. And listen, you have to go through Newton's laws. It's a must. And center of gravity, friction, linear motion, right? Those are very much linked to the coming parts, right? Very much linked to the coming parts. So go through all the things before you come into the next class, because when we solve applications, all these knowledge are coming into play, and you have to use it on a single question, in a single question, collectively, right? Even friction, no? Even friction. So when it comes to rotational pulleys are tough. Otherwise, pulley is not going to rotate, no? If there is smooth, string is slip. So therefore, when rotational pulleys are given, they are rough, right? Then friction comes. They are from pulleys, no? Then very much similar to the applications we did in pulleys in Newton's laws, right? And if there are linear motion parts are coming, right? About center of gravities, there are applications, right? So likewise, different things are there. So therefore, mainly go through linear motion, right? Vectors කොහොමද ඕනේ? ඒකත් කියනවා. Linear motion, vectors, listen, linear motion, vectors, Newton's laws, center of gravity, friction, right? Mainly these 5 are linked to rotational motion, right? So it's a must to know all the things before starting all the applications. So therefore, go through everything and come to next class, right? So next day we will be spending most of the time with the applications of this, and there are more new theories are also to be learned. So we will learn those theories along with the applications, right? Okay, so this month, for the month, the plan is we are in rotational motion. So first we'll complete rotational motion. Usually it takes around 3 days for rotational motion, right? Around 3 days. And after rotational motion, we'll be starting circular motion, right? So those are the coming up parts, right? Now we are getting closer to the latter parts of mechanics, right? Now there are only 3 topics remaining in mechanics: circular motion, hydrostatics, and hydrodynamics, or we call fluid dynamics. Only 3 remaining out of 11, which means 8 are already done. I mean, now we have started rotational motion, no? So with rotational motion, 8 subunits are done already in mechanics. It consists of 11, right? Starting from linear motion, like linear motion, projectile motion, vectors, linear momentum, Newton's laws, linear momentum and energy. Likewise, there are 11 friction, center of gravity. There are 11, right? Okay, then if no any questions, okay, it's clear now, no? Right. If no any questions, we'll wind up. Stay safe and go safe. And as I told you at the beginning, so make this year fruitful and make this year, make use of this year throughout the year until you are sitting for the exam, just 19 months now, and get the maximum out of this and start your things and do work in a consistent manner. Consistency is the key here, right? Do work in a consistent manner. It doesn't work if you fluctuate it, right? If you do it in a fluctuating manner, this is not going to work, because if you do like this, you are studying for 4 hours one day and nothing at all on another day, 10 minutes another day, right? 3 hours another day, right? 5 minutes another day. The average is somewhere very low, not going to work. So always you have to keep up the consistency. So you have to keep up this consistency. Once you have consistency only, you will go up along that curve that I mentioned, the exponential growth, right? So therefore, make this year, make use of the year starting from today, and you have to continue this rhythm, this momentum that we have, the rhythm we have when working until you are sitting for the exam, right? There's no way back, or there's no like coming back or looking back when we are in this game. This is a game. A-levels is also a game. It's like a match, right? So you have to play the game. Now you are on the court now, and you have to play the game. Court level. So if you are just spectating, you have to be in the audience, right? Then in the court. Now you are inside the court, right? You have to play it. Now if you are inside the wrestling court, you have to play, no? Something like that, right? Then to play it, you have to improve your skills, right? Right? It's like wrestling. Make a game now. This is a match. This is a game, right? Then to play the game, we have to gain skills. Now if you are playing wrestling, you have to know wrestling. You have to gain skill. Wrestling done na angam perpuluhan ke wrestling kan na karate puluhan ke wrestling ben, right? Karate kada lane naga wrestling ka makare. It's different. Now doing physics means you have to do physics in the way that we should do physics, right? Okay, so make this your year. That's the thing. Starting from 26, right? So whatever you do so far, forget about everything and start fresh from today. I mean this year. Right? I mean, කලින් නිකන් ඔහේ බලන් හිටියද? ඒ කියන්නේ maybe you are wasting time throughout the day without doing anything at all, right? So just forget about your behavior. I mean, forget about everything means behavior, not the academics, right? Forget about your behavior and focus on improving yourself and make a new version of yourself starting from today, right? Starting from today. Make a new version of yourself, right? Okay then we'll wind up. See you all in the next class. Stay safe and go safe. Good night and goodbye.